If the weight force is 500 newtons and the normal force is 450 newtons on a box that sits at rest on an incline, what is the angle of the incline? So many physics problems, it's a good idea to start by kind of trying to sketch what the situation that's described looks like. And so I'm going to attempt to do that here. This line, I'm going to have that represent my incline, and then I'm going to kind of try to draw a box on it here. Fortunately, boxes aren't supposed to be that hard to draw, right? But I'm not very good at drawing. And that box is sitting on that incline at rest, and it's not sliding down because we're not going to assume no friction here. This box is kind of, there is enough friction to kind of hold it. There is kind of maybe the picture of this situation. And we're given, again, these two forces, but I think friction is going to be part of the story here as well. So to kind of tell the story of the forces, this is the part that we're really learning how to do in this chapter, is to figure out forces based on some ideas surrounding them, some rules that we're establishing for them. One of those rules is that the force of gravity is always on Earth going to point straight down. So I always like to start with that one because it's straightforward. It's always the same. Pretty much, unless maybe a really novel situation, it might not be the same. But for on Earth situations, and if you don't draw your picture kind of wonky, it's always going to be that. What about the normal force? Does it always have to point up? I mean, we've seen in some previous examples that it has, but really it needs to be at right angles to the surface that is supporting this box. That's why it's called the normal force. So I'm going to draw the normal force in here and attempt to draw what I think is at right angles to the surface of the incline. Now, if these were the only two forces there, I think this box wouldn't stay in place. It would slide down. There also needs to be a friction force. And intuitively, I'm going to put that friction force. It turns out we're going to develop later on some more explicit rules. We're going to have to sort of be able to list all the rules for these forces. Generally, friction will oppose the direction an object would want to move in if there were no friction. And if you imagine this incline just being made out of like really slick ice or something like that, we all know what the box would do is it would tend to slide down. So the friction force opposing that should point in the opposite direction. And generally speaking, friction forces are always parallel to the surfaces that are kind of experiencing friction with one another. So I'm going to put that into my diagram there as a force of friction. And then let me look at the question. The question was to find the angle, right? And the thing that we're given, I can also put in what we're given here and say, okay, force of gravity is 500 newtons, and the normal force was given to us as 450 newtons. It might kind of make sense why this one's a little bit less than gravity, because this object is supported not just by the normal force from preventing from like going into free fall, but also this friction force kind of picks up some of the slack. Unfortunately, we're not given any information about it, but we are asked to find in the picture of the situation, I can say this angle right here, I think is the angle that we're being asked for. So I'll put a question mark right there for that. So how can we figure this out? Well, one of the things, since this box is at rest, I'm going to write here that at rest, following Newton's first law, if it's at rest, it has to be that the net force on that object is 0. And one of the other ways we have of saying what the net force is, like I could have also said, really the sum of all these external forces must be equal to 0. So that means the vector sum of these three forces, right? And I don't want to spend too much space here stating this, but another way I could state what I just did, I'll just put it in the kind of space up here, is that explicitly f sub g plus f sub n plus f sub f must be equal to 0 as a vector equation. And we've seen there are multiple different ways of handling vector equations, but what I can do with this one is I can say, could I move these vectors around and get like a geometric interpretation of this? In other words, maybe, I don't know, should I do it in order the way it is? Hopefully that'll make sense. If I start by redrawing that force of gravity down, I'm going to make it maybe a little bit bigger than I had originally. So I'm following this equation here. I'm saying there's f sub g, and then head to tail. Next we're going to do f sub n, which pointed out kind of a different angle there, maybe something like this. So that would be the f sub n vector. And then head to tail here, I think I'd complete this kind of setup with the friction force. So again, this was f sub g, f sub n, and this is the geometry that describes the sum of these three forces adding to 0. So how does it say that it's adding to 0? When I arrange them head to tail, I return to the same spot. So that meant the resultant force of that sum is, there is no space there, so that basically it's a 0 vector, you could say. So this geometry, though, is going to let me answer this question, though, because I think if I look at this setup here, it might make sense that this angle right here, that the normal force, the normal force was a little bit slanted away from vertical, and the amount that it was slanted away from vertical, I think, has to be the same as this angle right here. Well, that angle right there, I mean, again, that's the amount that the normal force was slanted away from the vertical. That, I think, has to be this angle right here in this triangle. Now, if I redraw this as a triangle here and I say, okay, so here's the triangle I just drew, right? That's kind of in this force diagram. This is the triangle that those forces kind of made up, right? And this was the angle I'm looking for, so maybe I'll call that theta. There's a right angle here because the force of friction and the normal force were at right angles to each other, and we know that the normal force had a value of 450 newtons, and we know that the gravity force had a value of 500 newtons. So this makes a right triangle with a hypotenuse of 500 and an adjacent leg to the angle I'm interested in of 450. So that means that the cosine of that angle must be equal to 450 over 500, which suggests that the angle I'm interested in would have to be the inverse cosine of 450 divided by 500. And maybe now it's time to get my calculator and see what number that gives me. And that gives me 25.8419, etc. But maybe I can just round that off to 25.8. I'll put a little degree symbol here. Oops, make sure your degree symbol doesn't look like a 0, right? Anyways, let's see how close that is to the answer that the slides give. The slide actually is going to give us a little bit of a picture here as well and show us the FBD. And there it is. There's gravity. There's a normal force. There's that friction force I had to add because this was trying to be realistic. And then all at once, it just showed the answer without maybe quite as much of the details that I showed over here. But we got a match of 25.8 degrees out of that.